Shall we begin? Are you guys all ready with your caffeine and all the good stuff that you require in Vegas to keep you awake? I know sometimes caffeine doesn't work. It doesn't work for me. I like Sprite. That kicks in right away for me. So, good morning, everyone. Okay. I believe still there are folks who are not up on caffeine. I'll repeat again. Good morning, everyone.
Good morning.
Awesome. So this is what I need during the whole session. If you have any questions, raise your hand, post the questions. I believe and I hope you are in the right session. It's on troubleshooting end-to-end MPLS. My name is VinitJain. I work for HTTS, High Touch Technical Services. I'm one of the technical leads there, troubleshooting day and night on routing protocols, MPLS, multicast, anything related to routing on iOS, iOS XE, Nexus. Sometimes I even touch XR. I used to work on XR dev testing for some of the features back in the days. Apart from that, we support premium customers of Cisco. Been working with Cisco for near about 7 years. And during the course, I have attained some CCIs, but the number still remains the same. So, it doesn't change. This session, if you have any questions, and if I'm not able to answer during this presentation, you can follow up with me on Twitter, and I'll be more than happy to respond to you with all your questions answered over there. Or we can meet at the end of the session or in the Meet the Engineer section to take all your design or troubleshooting issues related to MPLS, and I'll be more than happy to take those questions as well. Okay? I will also request at the end of the session, do pull in your feedback. It's really important, and we take it very seriously. I used to present on troubleshooting BGP for last 2 Cisco Lives, one in Berlin, one in San Diego, and I took this feedback so seriously that I actually authored this book, Troubleshooting BGP, in which I'm covering near about 600 to 700 pages of all BGP stuff, from basic BGP to MPLS VPNs, L2 VPNs, wherever BGP is involved, VPLS, all the stuff related to BGP is being covered in this book. So some of the content that you see here today as well, and wherever it's related to BGP, this book is the go-to for you. In today's presentation, we'll be talking about few of the interesting topics. I'll be covering upon some of the basic stuffs, basic concepts, which are required to build a base on MPLS. Apart from that, we'll be discussing on a lot of troubleshooting scenarios which you commonly see in your network. And we'll be seeing how we can troubleshoot them and how we can overcome those issues so that you minimize the amount of outage situations or traffic loss situations in your network. Okay? So we'll be beginning with some of the fundamental stuff to build up the base, to set the stage. Then we'll be seeing how you troubleshoot LDP peering issues, which are pretty common, and they actually cause a lot of traffic loss during convergence. So how you can mitigate those. We'll be seeing how we can troubleshoot MPLS LSPs, label switch paths. Then we'll be moving on to troubleshooting MPLS L3 VPNs and IPv6 VPNs, which is 6VPE. And finally, we'll be closing off with inter-AS MPLS VPNs. I know it's not covering all the topics. Well, it's only 2 hours, and I can speak about MPLS the whole day. So it's not enough, but I'll try to cover as much of the content from the MPLS perspective, and if you have any other questions outside of this, you can still post it, and we'll take it. All right? Are we good to go? All right, with quick show of hands, service providers. Great. Enterprises with service provider, with MPLS or service provider for say. Okay, great. So this session is definitely for you. But all those who are preparing for CCIE, service provider or route switch, great. So this session also covers a lot of troubleshooting scenarios that are applicable for the CCI preparation as well. So it's really helpful. It's an advanced class, but we'll also be touching on some of the basic concepts, like I said before, but I'm assuming that you know how to configure basic MPLS, right? I'm also assuming you know some of the basic show commands and what they do, but there are certain show commands which are pretty common even for basic stuff, and we'll be discussing what their importance is and how they're actually populated so that you understand if there's a problem with a certain output, what you need to look at on the other side, okay? So, are we ready? Yes, good. So MPLS fundamentals. So usually, this clicker doesn't work. All right, so MPLS fundamentals. From the architecture perspective, most of the routing protocols, we deal with the control plane. And the forwarding plane is there on the router based on how the fib is and how the hardware is programmed, all that stuff. From the MPLS perspective, it's divided into two components. The control plane, data plane. First, the control plane is populated. The control plane is actually built using the routing protocols that you're using underlay, like OSPF, ISIS, EIGRP, whatever, to exchange the routing information or building the routing information base, routing table. And then how you form the data plane using Ceph and the MPLS labels. That is what it's all about, right? So these are the two main components that actually construct the whole architecture of MPLS. It's very easy. If you know the routing concepts, MPLS is going to be super easy for you. All right, so there are a few of the keywords that I'm going to use from time to time during this session, which is really important. If some of you are not aware of these, it's good time to have a refresher. RIB, routing information base, nothing but the routing table, okay? FIB, the Ceph table. iOS XR platforms have Ceph, so it's the Ceph table that it's populated. That's based on it. Lib, the label information base, where the label bindings are put together, okay? The LFIB, how the label information base is used to program the forwarding or construct the data plane for MPLS packets. And finally, the FEC. FEC is nothing but it's the same kind of packets that are forwarded across the whole path, and router treats them in the same way. Okay? Like I said, group of IP forwarded packets in the same manner. So same kind of packets. It may be a traffic engineering tunnel. It may be a regular IP packet. It may be a tunnel packet or MPLS packet, for say. Okay? So any of these. So these are the 4-5 terminologies which are really useful. Now we'll see how to build up the whole stuff. Sorry for design, but we'll see how the control plane is formed. Now first, we have the routing protocols database. Now, routing protocols database is actually used to formulate your whole RIB. Okay? The RIB is the routing table. So routing information database is like when you peer with two devices, like OSPF is running between them and you are exchanging routes, you form a database within that routing protocol or for that particular routing protocol, say for EIGRP or OSPF, ISIS, whatever it is. Based on that, the information is then transferred to the routing information base. After that, there's LDP. Now, when you peer LDP between two devices, it will give you bindings of the next hops or the connected networks on that other peering router. That bindings are exchanged between the two peering, LDP peering devices. That forms the lib. So far, so good? Once the lib is formed, now comes the data plane part. Now, based on the routing information base, you get to see the FIB, the forwarding information base. So the information from the routing table is downloaded into the Ceph table, and your hardware is programmed accordingly. So for ASR 9K platforms or any of the newer iOS platforms as well, like ASR 1K or ISR 4300s, where hardware switching is supported, all that information is downloaded into the Ceph table. Okay? Now, based on this fib table, and also based on the lib table, so the information combined from both these tables, the fib and the lib, we form the LFib. Means the forwarding plane, the forwarding information for the MPLS labeled packets. Okay? Now, what we have is, like I said before, the routing updates are used to form the routing database. Now, when there's an IP packet that enters the network, regular IP packet, okay, it looks into the fib table and forwards the packet. Now, it depends on what kind of forwarding it is. The next hop, it may be MPLS enabled, or next hop may be just regular IP. So based on what the treatment is, the packets are forwarded. So if there's an MPLS packet that enters the network, it looks into the LFib table. Not the fib table, but the LFib, because LFib is built based on the fib and the lib values. So we need to understand what kind of packet enters the network and what lookup is done at which point. So if there's an MPLS packet, LFib is looked up. If there's an IP packet, fib is looked up. Good? All right. And the result can be either an MPLS packet or an IP packet. So sometimes the next hop, MPLS packet enters the network. It may exit out as a regular IP packet. Depends on how the next hop or the label bindings are shown. Right? But the label bindings, again, if the next hop is an IP packet, the label bindings will be there in the lib and thus the programmed LFib. So again, the lookup will be the same. If it's an IP packet, regular IP packet, the lookup forward. Good? All right. So the MPLS header. Why we are discussing the MPLS header is sometimes we need to capture the packets within our network to understand what is going on. So if there is MPLS VPN scenario that you have deployed in your network, it may so be possible that you might not be able to see some of the customer packets if it's actually reaching to a certain point. Say for your customer is facing a traffic loss, right? He's not able to reach the remote site. How do you troubleshoot? So sometimes you might have to look at the sniffer traces or another tools which you can use to capture the traffic. So in that scenarios, this is useful. So the MPLS header contains 4 sections. One is the label, which is the 20 bits, the COS or the experimental bit, which is the class of service used for QoS values, S bit, which is for the bottom of stack, means as the last label in the stack, and the next hop should be IP forwarding. Okay? And then is the TTL value. This TTL value is actually used similar to routing protocols or the regular IP packet used for avoiding loops in the network. So same thing. Okay? And this guy actually is referred whenever you do a sniffer capture. Regular IP packets or Ethernet headers are looked at as 0x0800, whereas MPLS headers are actually 8847. And I'll show it to you where you can see this value later during the presentation. Okay? So far good? Guys, I need some voice. I need some energy. Awesome. All right. Now we have the MPLS label stack. Now there can be not just one label in the MPLS network, but multiple of them. It can be 2, 3, 4, 5. It depends on what scenario you're deploying in your network. It may be MPLS VPN with regular LDP, just 2 labels. Okay? It may be something more than that. Like you are deploying traffic engineering. So MPLS with traffic engineering. And then on top of that, you have fast reroute. Well, I'm not discussing traffic engineering fast reroute in this session, but I'm just giving an example where more labels are allocated and the stack is built on top of it. Okay? Then you have another scenario where you can have MPLS VPN with LDP and your traffic engineering or fast reroute. You can have 3 or more labels. And especially a scenario where you have custom carrier supporting carrier. I believe I was speaking to one of you where you guys were deploying CSC, right? So in those scenarios, you can have 4 labels or maybe even 5, based on, again, what scenario you're deploying. If you are having TFRR and customer and carrier supporting carrier, you can have 4 labels. If you have, like, between the carrier provider and your super backbone LDP neighborship, and then on top of it, your TFRR, you can still have 5 labels. So those are different scenarios. Okay? But the treatment remains the same. How many number of labels are there in the stack? The forwarding, the lookup, the popping, swapping, addition of the labels, it's always the same. Nothing changes. It's only the deployment that changes the stack. Good? All right. Now, from the label switch path, now what is label switch path? A path where the packets will be label switched rather than performing an IP lookup. Okay? So your shortest path within your network, it may be possible that it may be taking 3 hops, but your label switch path may be taking 4 hops. It may be totally different. It may be ABC for the IP path or regular SPF, shortest path, and it may be BCD or ABD for label switch path. So it depends how your label switch path is formed and how your routing is, and based on that, your forwarding or the path will be formed. Your label switch path will be used. Again, this is unidirectional, so LSPs from A to C and C to A are 2 different LSPs. But you require the LSPs on both sides for proper communication back and forth. All right, quick check. Which of these protocols do labeling and signaling? Goody's waiting for you, and all those who know the answer will not answer. Will have or will not? Okay, there'll be something for you at the end of the session. We'll meet one-on-one. All right. So this is what I was covering from the fundamentals part. I mean, just touching base on what MPLS is all about, and now we'll actually deep dive into the troubleshooting scenarios. You guys ready to go? Awesome. So LDP configuration on iOS or ISXE. I'm just touching base upon the configuration because there's a whole lot difference between configurations on different platforms. So you just configure MPLS IP and set the label protocol to LDP under the interface, or you can set it globally as well, MPLS label protocol LDP on the global configuration. When you go to ISXR, there's no TDP, which is there on iOS. In MPLS iOS what you do is you go into the MPLS LDP section and you enable the interfaces, just configure the interfaces. This is hierarchical in iOS XR, so it's pretty easy and easy to understand which all interfaces are MPLS enabled, okay? But remember, for iOS XR, you need MPLS PI to be installed. In Nexus OS, and this is very interesting, you first need to install the feature set for MPLS, or even for MPLS L3 VPN or L2 VPN. Then you need to enable the feature set for MPLS, and then you can enable the feature for MPLS to work, like MPLS LDP or MPLS traffic engineering, your L3 VPN, all that stuff, then you can enable it. But you need to follow the first 2 steps. If they are not done, you will not even see the option for feature MPLS, okay? Once the first 3 steps are done, it is then you can use MPLS LDP configuration and then configure the regular interfaces with MPLS IP like you do in iOS. But without that, MPLS IP configuration will not even be there on Nexus. So, just for using it. So again, touching upon some basic stuff, TCP port 646. Now basic discovery, it is done based on the multicast UDP hellos, right? And there is targeted LDP sessions as well. Targeted means not directly connected, but different hops away. Like A, B, C, A and B are peering together or forming a LDP neighborship. They are regular basic discovery part. If they are A and C are forming the LDP or targeted sessions, that is targeted LDP. Okay? In this scenario, you send a packet or a hello targeted to the destination rather than just to the connected device. These are the default parameters. You can tweak them, but when you do that, ensure you do it across your network so that it's it's stagnant and same consistency is maintained across your network, but some part of the network you want them to be aggressive, a bit aggressive, so you can tweak them. But you need to ensure you do that on both sides. And there's a command for show MPLS LDP parameters to look at those values. Whatever is configured. You do not need to do show run pipe include MPLS all the time to look at those. Now here's a sniffer capture on how the LDP neighborship looks like. So if you look here closely, you see the first hello message, okay? The first hello message sent from one of the peers 10.1.111.11. The other one also sends the hello message from 10.1.111.1. Both sides receive the hello. They start the TCP negotiation, okay? On the port 646. They send the SYN packet, the SYN ACK, and the acknowledgement back. Once that is done, your LDP neighborship is formed. That simple. But UDP hellos that I was talking about, it is in the first two sections. And those hellos keep going on during your, as long as your neighborship is always up, or even any of those sides are MPLS enabled. If you do not have MPLS enabled on one side, you will still keep getting the hellos from the other side because it is enabled on the other side. Okay? So if you're using some platform captures or like on 7600 NetDR or on ASR1K EPC embedded packet capture, you can actually filter your packets for the specific source and the destination for the multicast address. And based on that, you can actually see if you're receiving the hellos. So in case you're having LDP down situation and LDP neighborship never forms, use this, or the platform captures. How your LDP neighborship looks like. When you do show MPLS LDP neighbor, you can see the local and the remote peer device, okay, the remote peering IP, the TCP connection, who is peering with the TCP port, who is having the port 646, and the other side will be a random port, okay? The LDP discovery sources, what are the interfaces where it has been discovered and where it's forming, and at the bottom you will see the bindings. Address is bound to the peer. So the peer advertises its bindings to the first side. So A and B are peering. B advertises all its bindings to A, and A, from A, you can see this information, okay? You also need to ensure your TCP session is in established state. If your TCP session is not in established state, that's where you need to troubleshoot next, if your TCP session is getting blocked or not. Right? So in this part, what you can do is when you're having LDP router ID configured like loopback, do a ping from loopback to loopback rather than just doing from the physical interface. Sometimes the reachability may not be there. So it might be possible that you configured a new router and you forgot to enable OSPF or ISIS on the loopback interface, and you still set the router ID as the loopback in that scenario. And what you can do is, as a quick test, to ensure there's no ACL blocking the TCP packets for 646, you can use the telnet to the remote peering IP on port number 646. But ensure you set the source interface. So good? Okay. LDP router ID, what is its important, right? Usually what happens is if it's not manually coded, it looks into all the operational interfaces, even if it's a loopback interface, and whatever the highest IP address is, it uses that. But what happens is, in scenarios where your LDP is not hard-coded, you configure MPLS LDP router ID XYZ, and that interface is not up. Or it's up, but it was a different router ID before, and that interface is not down. In those scenarios, the LDP router ID will not change. So either of these scenarios, unless the interface of the new router ID is up and the existing LDP ID, which was there before, based on the selection process, is down. Unless this is the scenario, it will not take into effect. The only way it will take into effect is if you use the force keyword at the end. MPLS LDP router ID force. Okay? Now, the discovery part. Now, what happens is you want to ensure that when your LDP session is negotiating or your LDP negotiation is already done, you need to ensure that your hellos are continuously going through. You do not want the LDP session to flap randomly in your network, right? So what you want to do is ensure two things. In the show MPLS LDP discovery command, you need to ensure it is an exmit and receive, transmit and receive. It is transmitting the hellos and receiving the hellos. If it is not, there's a problem. And what kind of problems can we run into? We'll see next. This is the problem. So if you see here, there are the two routers are having LDP neighborship. So both sides, you see, it is an exmit, right? How you debug this? You can debug it. I mean, though I don't personally recommend to run debugs in the network, but in this example, I'm showing it just from the simulation environment. So if you see debug MPLS LDP transport connections, this is the command, the debug command that you actually use for debugging any of those hello issues, the connection issues. And if you see, it says scan listening for TCBs, but it never shows any other value, any TCP negotiation for the LDP session. It never shows that. Why is that? If you look closely, both the command outputs, there's one side it is TDP, because there might be some old routers still there present in your network which do not support LDP. By default, they support TDP, and you have to manually set them as LDP. There were those scenarios, and there are still some scenarios. But when you have such scenario, or one side you have MPLS IP configured, the other side you do not even have that. Even in that scenario, one side you will always see exmit, not receive. It's not receiving any hellos from the other side. In that scenario, ensure you configure MPLS IP, but if it's TDP configured, go into the interface mode and say MPLS label protocol LDP. This will fix it. This other similar scenario that you run into is, by the way, both the examples that I'm showing right now, those will have LDP down. If the LDP is down and the discovery you're seeing is these scenarios, that is the problem that we are discussing right now, okay? So in this scenario, you can see LDP session is not established. So if you do show MPLS LDP neighbor, you do not see a neighbor. But when you do a show MPLS LDP discovery, you can see it is an exmit receive. Other side is also exmit receive, means it's receiving hellos, but it's not forming a session. But you closely look at it, you see there's no route. What do you do next? You look at the routing table and see show IP route, the loopback ID of the peer device, and it's not on the table. This is a scenario where you have, for troubleshooting purpose or for bringing up a new service or maybe preferring a path, you configure a default route. In that scenario, you will run into this problem. So always look for the show MPLS discovery output, and it will show you there's no route. Okay? The next scenario we are going to discuss is sessions are not coming up. You look at the first side, you see show MPLS LDP neighbor, nothing there. The discovery part looks good. You can see the exmit and receive. You look at the routing table, that looks good as well. Now, you look at the other side. Obviously, there will be no neighbor. Then you look at the discovery, it looks good as well. The third thing you look at is the routing table. Now look at the first output on the router 1 and the other one, the P1 or the P1 router, right? There's a difference. The other side is learning the prefix via OSPF or ISIS. The another side, the P router, is actually receiving a summarized route, not the exact prefix, the specific prefix. This is going to lead into this problem. So if it is recommended, do not summarize the loopback IDs, okay? When you are running XR, you can use the commands like show MPLS LDP trace, and you can use for the peer or for the discovery and look at the traces and understand what is going on, because the XR boxes or even the Nexus boxes have event history or the traces. which can actually show you what events went through that led to the LDP session to go down. Okay? So in this scenario, if you look at it closely, you will see receive notification from the peer saying, keep alive, timer expired. Well, obviously, because the route is not present. It's looking for a /32, but it's not getting it. It's looking for the loopback ID, it's not having in the routing table. So keep alive, timer expired. Okay? LDP IGP sync. How many of you have deployed in your network? Are you looking forward to deploying your network? Or you know what LDP IGP sync is? I know Srinivas was discussing about it yesterday, but okay, so what it is all about. What happens in your network when your LDP, where your link flaps, and both the IGP and your LDP are in race? There's always a race, right? Too much competition is not good. Too much racing is not good, right? So the same thing here. If your LDP and IGP are in race condition and say IGP wins, it will start forwarding the packets, whereas your LDP is not even up and you don't even have the bindings, you don't even have your LSP path complete, your packets will get dropped. Because whenever there's an MPLS lookup and the MPLS table doesn't have the information, it says drop. Okay? So this is where LDP IGP sync comes into play. It says that do not start forwarding those MPLS packets as long as both my LDP and my IGP are in sync. Okay? This is what the solution looks like. So when the link is up and the LDP peer is reachable, or when the link is up and the LDP peer is not reachable. So there might be an alternate route, there might not be an alternate route. Depending on those scenarios, your router will take the decision. So it might say, defer the IGP adjacency, or it may also say, or if the alternate route is not available, it'll say, or it will advertise a max metric LSA towards the upstream devices saying, I don't have my LDP and IGP in sync, or I don't have an alternate route to my LDP peer. Just don't forward those packets across this path. Just don't do it. I don't need them. I cannot do any action for those. I'm going to drop it. Okay? This is what is going down. If the LDP session is down, it will again advertise the max metric. So no forwarding of MPLS packets across that path. This is how the configuration looks like. MPLS LDP sync, this is what you configure under your IGPs. So either it's OSPF or ISIS. And you can use, if you're using MPLS traffic engineering in your network, you need to use this configuration, MPLS LDP sync IGP shortcuts. This is only in the scenario when you're using MPLS traffic engineering. Otherwise, you don't. So far, good? Yeah. Sure. So the thing is, it may not have a targeted LDP session. Those are scenarios, right? So I'm coming to that part next, the session protection part, okay? But that was a good question. So I'm not sure if you guys heard at the back. The question was, if there's an alternate route present, why do you need to defer the IGP adjacency rather than just using the alternate route? The thing is, there's no targeted session using the alternate path at this point. We are assuming that is the scenario, okay? To have the alternate path or to protect that session even from the direct link going down, we'll be discussing the next scenario after this. That is this LDP session protection. So you're good with the configs, right? You can also set the delays under the MPLS LDP or just with the MPLS IP IGP sync delay command on iOS boxes. And the delay is set based on when the session is up or on the process is restarted. Well, the process restart concept comes in specifically on ISXR because LDP or any other protocol is just run as another process. So in those scenarios, you want to run this. Yes, sir?
We've had some cases where we've had to turn off
okay.
the sync.
Okay.
The OSPF wouldn't bind unless it was off or established.
Okay.
Haven't figured out the specific
Well, usually,
something, maintenance happened and
right. So usually this happens when your software doesn't work as expected, or your IGP sync is not working as it's supposed to be expected. Those are, I would say, the software glitches, but rather than the feature issue. All right. So the LDP session protection. Now, ma'am, to your question was, what if there's an alternate route, but the LDP or the link went down directly between the two devices? So you have 3 routers, A, B, C. The link between A and B went down, and you still have reachability to C via B from A. What you can do is you can actually form a targeted LDP session. Why can't you do that, right? Your session will still remain the same, but it's targeted and taking the alternate path. We want that feature to overcome some of the challenges even when you do not have you have an alternate route, but you cannot use it, okay? So in that scenario, what you do is you set up a targeted LDP session, you enable session protection method, and what it does is it sends a targeted hello as a backup towards the remote peer, so that in case the primary one goes down, there's an alternate path which is capable of maintaining that session and forwarding the labeled packets. And how does it look like? So the same thing that I was talking about, you have 3 routers, primary link went down, you have an alternate path, and you form a targeted. Just remember one thing, when you have targeted the session protection enabled, it's always a good practice to accept targeted hellos. So configure the command MPLS LDP discovery targeted hello accept. It's good to have it. Okay? Any questions? Yes? Right. Yes. So as long as you have the reachability and you have your session protected and you are accepting the targeted hellos, yes, it will form the LDP, targeted LDP session. With session protection, it is already there before as a backup. So when you do show MPLS LDP discovery, you will be able to see there. Any other questions? Yeah. Oh, what is that?
So the slide shows session protection, but you also need, like you mentioned, to do with global accept targeted hello. So the absence of that global command would negate session protection.
So what happens is usually in the networks, you may not have session protection enabled everywhere, but you might still want to have targeted sessions based on your EO MPLS circuits or any of those L2 VPN scenarios, or even traffic engineering scenarios from provider edge router towards the provider router. And in the middle, there's a broken LSP, and you want to patch the LSP. So that's where you use targeted hello accept, right? So you might want to have targeted hello accept, but sometimes what happens is not everywhere, every part of the network. So, and you usually use session protection on critical nodes where you don't want those, or you cannot afford to lose the LDP adjacency. So it's better to have those. And I think it should be present whenever you have LDP session protection enabled. All right, should we move further? You guys still up or need more caffeine? I can start jumping. All right, so now we'll troubleshoot MPLS LSP, label switch paths. For some reason, this clicker doesn't work. All right, now before we move further, let's consider one topology, okay? To make it easier so that we can correlate all the outputs, different outputs at different points. There's a C router, P1, provider router, and P2 router, remote P router. When I say remote P router, it will usually be P2, okay? When I say local P router, it will be P1. And the remote C router, which is C2. They are having MPBGP, that is MPLS VPN setup between P to P, okay? And there are the loopback IDs. So P1 is having 192.168.1.1, remote P.22, and the core device you can have anything, okay? Now, what are the different reasons when you can have broken LSPs? Say you brought up a new MPLS VPN customer on a new device, and you forgot to enable MPLS on one of the links. So the LDP adjacency is broken. Your MPLS is not enabled. Your labels are mismatched. So one side says my local label for a particular destination is, say, 20, and the router on which you're looking for the destination prefix is having 30. It's a mismatch of labels, right? It is usually caused due to software or hardware glitches. So what happens, most of the platforms where hardware forwarding is enabled, the LDP stuff, all the bindings, all the labeling stuff is first downloaded on the route processor. And from the route processor, it is then downloaded onto the CEF, on the line card, so that your forwarding doesn't have to go through the route processor all the time. Your line card is capable enough to do the label switch forwarding based on the labels. So no too much load on the route processor. Example, 7600s, RSP 720s, or you may have ES Plus line cards on 7600, ASR 9K platforms, ASR 1K platforms. Those are some of the examples, okay? So these things happen. Your CEF or the LFIB gets downloaded even on the hardware, and it's programmed in the hardware because they maintain their own CPUs, okay? Now, how is the LSP formed? The first thing to look for is the lib, and it's the most important component. Without your label bindings, you will not have proper LSP. So you need to ensure you have your local bindings and your remote bindings. So remote bindings is the bindings that you receive from your remote peer. Local bindings is the labels that you locate for the prefixes locally learned or learned from another device, but they will be forwarded across or through your device via label switched. So in those scenarios, you allocate those labels locally in order to reach that prefix, destination prefix. So those are the local and remote bindings. All the information, so by the way, quick question. Does LDP generate labels for BGP prefixes? We can be a bit louder. Awesome. So yes, no. The answer is correct, no. BGP generates label for its own prefixes. LDP cannot generate the BGP labels for the BGP prefixes. Now, how does the LDP bindings look like? Show MPLS LDP bindings. You will be able to see what bindings you are having, the local bindings for the prefixes, and the remote bindings that you have received from the peer. So when you do show MPLS LDP discovery, you will, or the show MPLS LDP bindings, you'll be able to see the remote bindings. But those remote bindings also has label information. That label information can be seen using this command. Okay? This label binding is used. Now, remember the diagram that I showed before, right? You have the rib, you have the rib, you have the lib that is used to build the LFIB. So the rib provides the prefix plus the next hop information because your IGP and all that information is stored there. And then once you have that information, rib says, so rib gets, LFIB gets that information from the fib, okay? Now LFIB says, I have the prefix and the next hop, and it says the lib, the label information base, for this prefix and the next hop, give me the in label and the out label. Once that in label and out label is received from the label information base, the LFIB is populated. And how does it look like? So first we look at the show IP route towards the destination. Once that is done, we look at the LDP neighbor. We ensure your LDP peering is there so that it has the LDP bindings. Then we look at the binding for the prefix that we are looking forward for. Once that is there, we further use the show MPLS forwarding, which actually shows the LFIB, the label forwarding information base, and says the local label is 20, and the remote label or the outgoing label is pop label. Now, if you see from the previous output from the show MPLS LDP binding for the particular prefix, you can see that the label is implicit null. Okay? That same label gets populated in the outgoing label. What the remote peer has assigned and advertised it to you, this is what you have as your out label. So these 4 steps actually help you at any point when you're troubleshooting MPLS issues. Remember these 4 steps and the diagram, you will never get stuck into MPLS troubleshooting. It's very important. MPLS OAM, not discussed much, but used heavily. How many of you use on a regular basis ping MPLS, traceroute MPLS? Yeah, we all use it, right? Wherever we are troubleshooting those MPLS crazy issues, forwarding not working or label switch path not complete. So we'll be discussing about it. So MPLS or LSP ping is actually based upon the same concept as IP, traceroute, or ping. Similar concept, but change in the behavior or change in the way it works. Okay? Here you have your MPLS echo request and your MPLS echo reply. Cool? And the information is actually based on the FEC. Now, what the ping does is it actually checks your egress router is having the same FEC that it wants to be. Okay? So test if a particular FEC ends in the correct egress LSR. If your ping is not working, it may be possible that your FEC is not the same across the whole path. It may be different. Now, FEC, from what I mean by FEC is, like, you might have a label switch path from A to B to C. At D, it is broken. So your FEC changes. It was a labeled packet, and now it's an IP packet. So your FEC changed. Same type of behavior, that's what FEC was. So if that is a scenario, MPLS ping will really help you. Traceroute, it actually helps in hop-by-hop isolation. So you don't know where the LSP is broken, and you want to figure it out where exactly it is, traceroute is the go-to-go. Okay? I will see how both of them work. Now, there are different options. Ping MPLS, traceroute MPLS. Now, you can do traceroute or ping for MPLS or multipath or traffic engineering. You also have an option for pseudo-wire for traceroute. It depends on certain platforms. Certain platforms have more capability than, and again, the code as well, which iOS or i6 version you're using and so forth. But these are the options. Now, how LSP ping works. Now, in the LSP pings, it actually verifies your data plane is actually working fine or not within your service provider network. Okay? If your data plane is working, your label switch path will always be successful. The only thing is, you go send an echo request, you receive a echo reply, and it verifies the FEC exit on the correct LSP egress LSR. What is the format of the packet? What it actually sends when you do a ping MPLS or traceroute MPLS? This is the packet. And the most important fields that you need to look for is the message type, the reply mode, return code, and the TLVs. The TLVs is where actually you specify what your FEC is. So different kind of ping test you're doing or different kind of ping MPLS options that you're using, based on that, your TLV will change. Okay? Your FEC will be changing. So what do we look for? The version number is 1. Message type, it can be either echo request or echo reply. Then you have the reply mode. In the reply mode, there are 4 options. We'll be seeing them next. Timestamp, and then you have your return code. We'll be seeing them one by one now. Now, what happens when you have a reply mode on and when you have the first mode that is do not reply? Now, it is usually when you have something called keep alive applications running on the remote peer. Right? In those scenarios, it is useful when you have your sequence number mismatchings or any of those things which is causing the LSP to break from the keep alive perspective, that's where the do not reply mode is used. The default mode is IPv4 UDP packet. Okay? This is the regular or the default mode when you want your LSP path to be responding to your MPLS echo request. Most common mode or most heavily used mode, the alternate mode is sometimes what happens is your LSP ping doesn't work. And you want to see, is your hardware is the problematic? It's your hardware programming messed up somewhere in the path, or your software is messed up. So how do you do that? You can use the router alert option. Okay? So when you do a ping MPLS, you will get an option to set router alert at the end. Okay? So far good? Now in this option, in the router alert option, what it does is rather than doing the switching, the hardware switching, it does software processing. So packets are actually punted towards the CPU and they are processed there rather than getting processed on the hardware itself. So this is CPU intensive, and you may only want to use it when you're troubleshooting LSP broken issues. Make sense? Make sense? Yes. Okay. All right. So these are the return codes that I was talking about. The most common used modes or most commonly seen in success is option 3. Means replying router is an egress for the FEC. That is what we wanted. When you have the destination unreachable, you have 4. These are the most commonly seen. 0 is something that is, can anybody answer it? In which scenario a router will set the return code to 0? Only in a scenario when you are initiating a ping from a router, the router initiating the MPLS ping will set the return code to 0. All the other routers will reply with the rest of the other codes. But no other router, apart from the one from where you initiated the MPLS ping, will set that. Okay? Any questions? Now, this is how it looks like. Now, if you want to see what was the return code, use the command verbose at the end, the keyword verbose at the end. Ping MPLS IPv4, the destination, the subnet mask, and verbose. And if you see, the reply is there with the return code of 3. If there's a failure, there are different return codes. Obviously, you do not want to, we cannot remember all those numbers, right? So it's made into much easy readable format, these codes. Okay? Now, operational theory. What happens when you send the MPLS ping? What is the destination IP? What is the source IP? When you do the MPLS ping, the destination IP is not the destination address. It is a loopback address. Loopback, remember Microsoft, loopback 127.0.0.1.2.3, all those IPs? When you do the MPLS ping, the destination IP address is always 127/8 address. Good? But the reply is reversed, but the destination address in the reply will be the source address. So 1.1.1.1 sends MPLS ping towards 1.1.1.2. The destination, when the ping request is sent, it will be 127.0.0.1, say. Reply will be 1.1.1.2 towards the source 1.1.1.1. Okay? And this we can prove it looking at this output from the sniffer traces. So if you look at it closely, you will see the MPLS echo request 10.1.111.1, and the echo request destination is 127.0.0.1. It can be .2, .3 as well within the path, but this is the one. And you see the echo reply, it is different. It is having the proper source and destination. Why is that done that way? Any reason? So that it consumes. So that the router consumes that address and forwards the packet back. Otherwise, it will not. So what happens is, if you do not have that address in your table, what it'll do is it'll say it's not reachable, reply back, but it will not forward it across. And it's required to be forwarded across, which we'll see further in the example. Okay? So with the MPLS LSP ping, we generate MPLS equal request. Remember, with ping MPLS, the TTL value starts with 255. With trace route, it's the other way around. It starts with 1, 2, 3, and so forth. Okay? TTL value always play an important role when you're troubleshooting MPLS or even routing, right? The last 2 points I already mentioned. Only the sender router will set the return code to 0. Rest, all the other routers in the path will set the reply or return code as a different value based on how their FEC is looking, how their response is. Now, TTL values or TTL fields in the label. If you have the TTL field as 0, the packet is dropped. No question. No further action on it. It is dropped. It's not forwarded. Either it's stripped up or rather forwarded as an IP packet. That may be another option. But if you have to complete or if you want to send a packet as an LSP packet, in that scenario, it will be dropped. Okay? If an IP packet is labeled first, the TTL value is actually copied onto the label, but after reducing with 1 from the IP header. So the TTL value from the IP packet came in as like 50. Your labeled TTL value will be 1 less, 49. But your IP packet within that labeled packet will also be 49. Okay? We'll see that. I know, from the theory perspective, it might not be clear. That's the reason I put together an example, which I'll show you next. So what happens on the receiving side? The receiving LSR checks the label stack of received packet and matches with the FEC. Like I said before, based on the FEC, how the router needs to reply, the LSR needs to reply, or the destination needs to reply, it will reply with the return code. If the FEC is not present, 4, destination unreachable. If the FEC is different than expected, another option, another written code, okay? Router alert option, I already spoke about it. So if there's a router alert option that you're setting when you're doing an MPLS ping, the router alert label is set on top of your existing label. So far good? Questions? Or is it too boring? You can say it. I'll make it interesting. All right. So router alert label, whenever you're doing a router alert option, it'll make it at the top of the label so that whenever the LSR sees the packet and it sees the router alert label, it will send it to the CPU for processing rather than switching it in the hardware or doing it hardware switched or Ceph switched. It will not do that. It will do process switched. So here's the scenario. In case, for some reason in your network, your router misbehaves due to a software or hardware glitch, and you see the CPU going high, you may also want to capture the packet getting punted towards the CPU. It may be possible, and I've seen those scenarios during TAC troubleshooting cases, that MPLS packets get software switched. You want to understand why they're getting software switched rather than getting hardware switched. So it may be possible your hardware is messed up, corrupt programming, or your software is having a glitch which caused that hardware programming glitch, and the packets are being punted towards the CPU and causing high CPU and impacting other parts of the network. You don't want that, okay? So sometimes if the CPU is high due to MPLS, understand what is going on, do an in-band capture, and look at the packet coming to the router. Now, the topology that we saw had this label information. So the P2 is an XR router, so it's having the VPN label for the prefix 172.168.2.2 as 24008. And the P1 is an iOS router, it's having a VPN label of 16 for the prefix 172.168.1.1. And within the core, it has its own IGP labels for going back and forth. So this part is already explained from the binding stuff that we discussed so far, okay? Now, how does the packet flow? This is important. I would request every one of you to pay close attention to this so that we can understand how the MPLS or the traceroute in the MPLS works. This will be really helpful to isolate any problem. Now, look at the first packet. The C1 sends a packet towards the destination with the TTL value of 2. The packet reaches the P1 router. When the P1 router sends the packets toward the P router, it reduces the TTL value of 1 of the IP packet, and also the same value is copied on the top label. Top label is IGP label. Okay? Guys, yes or no? Some more energy? Yes. Awesome. So top label is IGP label. It's same value of TTL as the IP label, IP packet. When the P router forwards the packet towards P1, P2, what happens? Obviously, it's penultimate pop. It will pop the top label. Only the VPN label is forwarded. In that scenario, after TTL value 1, it has to reduce, strip off the label. What will happen? The TTL is copied as 255, back to 0 from 255. The TTL value 255. Now, the packet initially had TTL value of 1. Now it is having 255. Did the TTL increment from what it was before? Yes, no? Please, yes, no? Okay. If you guys interact with me, it will be easier for me to explain you in a much better way. Okay? I request you, all of you. All right. So TTL value exceeded. Now, look at this. It says when you have the TTL value of the packet from 1 to 255, rather than sending that actual UDP packet, it replied or sending ICMP TTL exceeded. And it's actually forwarding it to P2. Okay? Now, when the packet reaches P2, it says it's an aggregate label for me for the destination, because based on the label 24008, it looks at into the VRF table, says aggregate label for the VPN prefix. I'll talk about the aggregate label further when we move to the MPLS troubleshooting or MPLS VPN troubleshooting. But so at this point, let it just be an aggregate label, okay? So it says aggregate label. What do I need to do? I need to do IP lookup, okay? The P2 router does the IP lookup and responds back saying, I have the IP packet with TTL exceeded. Now this will be the IP packet that will be responded. So the packet was sent as UDP. Response is coming as ICMP. So ensure ICMP is not blocked. Your MPLS trace will not work. Okay? Or even if the trace is done from the C routers, it might not work. So ensure it is not blocked, right? Now, the TTL was 255. It reduced to 254, one less. The same value is copied to the top label, IGP label. Moving to the next hop, which is P2 to P1. Now here, the TTL value from 254, stripped off label, reduced to 253. 253, but it will not change over here for the IP packet. It's only for the top label, okay? And when it reaches the C router, and if you do a sniffer capture, you will always see TTL, ICMP TTL exceeded responses rather than UDP responses, okay? And why it was, now the question comes in, when you saw the TTL as 255, why didn't we respond back towards the router, right? Towards the source from where it came, that TTL was exceeded. It's a problem, right? The reason is the source of the ping was, and the destination was, the VPN prefix. You cannot do a lookup for the VPN prefix in the core network on the P routers. So it has to forward that packet towards the P, remote edge router. And that router is capable of doing the lookup. Make sense? Okay. That's what I was looking for. Okay, now when the response comes back, the ICMP packets are treated with experimental bit 6 with high priority. Okay, now service providers, I know a lot of you would not want to expose what is there in your network to the customers, right? When customers will keep doing ping or different kind of things, crazy things, which you do not want them to be exposed to your network, right? What you do, you hide the hops or the devices within your network, and you always show them your device, remote device, and your router. You don't want to know what is there in my network. I don't want you, right? In that scenario, you need to use the command or disable the command MPLS IP propagate TTL forwarded. This is enabled by default, so you will not see in the running configuration, but you will see it when you disable it. And this is usually done on the provider-edge routers, so that whenever the packet hits in, it's not responded. I mean, it doesn't show you what the trace is within the network. Okay? We'll see how this works. It's important, right? You want to understand. Now, we saw how a trace works in an MPLS network. We also want to see how it will work when you have this feature enabled. Now, before that, when you do a trace with regular TTL-enabled command, you will see all your hops. We looked at the P router, the local P router. Let's look at it. The next hop is the P router. The next hop after that is the remote P router, and then the C router. All the 4 hops responded, right? We don't want that. We configured disable the command TTL forwarded, and this is what we see. If you see here, we have the local P router, the remote P router, because it has to do a lookup there, and then the C router. No information of what is there within your network, the P router. I mean, in this example, it's just 1 hop, but you may have hundreds of routers, right? You do not want to expose them. So this is what you configure on your provider edge. Now let's look at it and understand what is going on. So the C router sends the packet, the same packet with TTL size 2, UDP port number. Remember, this UDP port number is random. It has no relation that it's a fixed UDP port number. Okay? So let's not confuse that part. The packet reaches the P router. The P router says it reduces the TTL value to 1. Same behavior. But now you have TTL disabled. So it reaches the next hop. At this point, on the P1 router, the TTL value will become to 0. Agree? Okay. Next hop, it reaches P2. Remember, the bottom label, the bottom packet, the actual IP packet hasn't changed. The only thing that changed was the label TTL. Why? Because whatever the packet forwarding was happening, we disabled that, do not copy the information from MPLS to IP within the network. We disabled it. Okay? This packet goes further. At the edge, it says aggregate label. It needs to do an IP lookup and forwards the packet to CE2. Done? Now this guy, does it know what is UDP port number 35678? Probably not. So what it says? It's brainstorming and says, I don't know you. Port unreachable. This is what the reply comes from CE2. When this comes, this is the packet that is going to get forwarded across the path. Port unreachable all the time. The TTL value of the label. So the TTL was 1. Remember before, it moved to 255 on the return side. And the top label is again 255. What is there for the IP packet? The bottom layer. It moved to the next hop. The label TTL value reduced, 255 to 254. This ICMP port unreachable packet remains same. and forward it back to, after stripping off the label, forward it back to C1. So when you do a sniffer capture, you will always see port unreachable messages. Or if you do debug ICMP, debug IP ICMP on the C router, you will see this response. Okay? Good? Does it help understanding how the forwarding is working or how the trace is working when you have different scenarios configured? And does it help? Or you will have to test it to see if it helps. Okay. All right. Now, rest of the whole section is fun part. Trust me. It's all, yeah, you're going to have a party, right? It's all fun. It's all forwarding and real troubleshooting scenarios, what you look at each hop. And we'll see now, okay? Now, MPLS forwarding plane. One thing important about MPLS forwarding plane is you want to ensure your Ceph is enabled. I remember working on some of the cases like 2 or 3 years ago. Now, GSRs are not used that much. But a lot of times when the router used to get overloaded with a lot of prefixes, the Ceph used to get downloaded onto the hardware. The Ceph used to get disabled because saying, overloaded and the line card cannot handle those number of Ceph entries. In those scenarios, the forwarding used to get impacted heavily. Similar scenario back in the days when, I would say 1.5 years ago when there was an increase in the internet routing table. It surpassed 5 and 2K prefixes. That time 7600 also hit this problem. What was the problem was, the default for RSP 720 cards, I'm not sure how many of you are aware of 720, 7600s? Awesome. So you guys can correlate what is going on with 7600. So RSP 720s, they have the default MLS entries for IPv4 and MPLS packets to 512K by default. You can increase it to 1 million, but you will have to give up on the resources on IPv6 and other stuff. So by default, 5 and 2K, internet routing table, customers were pairing with the service provider to get the whole internet routing table. And as soon as there was an increase from 5 and 2K, it surpassed that limit, the forwarding got impacted. The Ceph was disabled. The only way to recover was reload. And even that didn't used to help because the internet routing table was still high. The only option was to increase the MLS entries on the router to the value that can handle all the number of IP routing table of the internet. Okay? So, by the way, 7600s are going end of sale this month. Not a good news, I know. All right, so Ceph needs to be enabled all the time. Ensure show IP Ceph, or whenever you run show Ceph commands on ISXR as well, ensure that you see proper outputs rather than saying Ceph is disabled, okay? Now, what you need to understand from this part is any packet that enters the MPLS network will do an MPLS lookup. Well, there are different scenarios, but if an MPLS packet is arrived and it requires label forwarding, it will do an MPLS lookup, okay? Now, the Ceph thing that I mentioned, if your Ceph is disabled, you will see no label binding received from the remote side, or you will see the outgoing interface as dropped. Or other alternate thing that you can look for is show IP Ceph for the destination prefix. It will neither show you the entry or neither show you the label information. It will say Ceph is disabled. Either of these three things, okay? So remember, whenever you look for the MPLS forwarding table or show IP Ceph, ensure the prefixes that you want your forwarding to work on doesn't have that drop adjacency. If there's a drop adjacency, you might want to look at the resource utilization on your router. Okay? All right. Now, we look at the LFIP. Like I said before, based on the outgoing label, the forwarding decision will take place. Okay? The forwarding outgoing label is the label that is a local label that was assigned by the peer router. Local label assigned by the peer router, advertised to my router as a binding, saying this is the label that you need to use to forward the packet. Okay? Now, there are 3 different outgoing labels apart from a regular numeric outgoing label that you look for is pop, untagged, and aggregate. 0 to 15 are reserved. For sure, there's no change in that. Well, iOS XR uses labels starting with 16,000 rather than starting with 16. Okay? Just for your information. All right. So when you look for the show MPLS forwarding table, you look at there are some prefixes showing as pop, some are showing as untagged, and some are showing as aggregate. When you see aggregate, it means you have labels which are allocated for VPN prefixes. So you have a P router, you have a VRF, and when you're receiving a prefix, you assign an aggregate label for the VPN prefixes. So you say convert an MPLS packet to an IP packet, because whenever the packet you receive from the MPLS side and you need to forward it across the VRF interfaces, it will do a right IP lookup rather than doing an MPLS lookup, right? So in that scenario, you will see an aggregate label. Pop label is when you want to pop the label, strip off the top layer label, and just forward the packet. If there's an IP packet at the bottom, it will do IP lookup. If there's another MPLS packet, like for MPLS VPN scenario, it will do an MPLS lookup based on that, either in the BGP labels or the LDP labels. When you see untagged, this is the fun part. Now, you might not have all the interfaces MPLS enabled. In that scenario, and your destination is part of that same interface, is going by the same interface. In that scenario, you will see untagged, means convert the incoming MPLS packet to an IP packet and forward it. I don't want to tag it, just untag what is there and forward it. But it is not as same as aggregate label, because there you convert it into an IP packet because the further forwarding is based on VPN label lookup. Okay? Any questions? Okay, I see it. I hear it. All right, so there are 3 different scenarios. I will revisit them again. Label imposition, disposition, and swapping. Swapping happens within the core. Imposition on the ingress P router. Disposition means stripping off at the remote P router. Okay? Control plane works opposite of the data plane. A to C, C to A. A to C is the control plane, C to A is the data plane. So, that way. Now, based on these 3 scenarios, the lookup will happen on different components. So, if it's a label imposition, it will say fib lookup, right? Because the packet came in as an IP packet. Now, if you have a label swapping, obviously it needs to look at the labels. So, LFib lookup. Again, if there's a label disposition, so it reaches the remote P router, it will have to do LFib lookup. Why? Because it will have a VPN label, and then it will have to convert it in an IP packet lookup. So it will again have to look up the information on LFib. 3 scenarios. Are you guys feeling sleepy? Looks like. A bit of noise, please. All right. I see we are up again. Okay. Load sharing. Now, load sharing is similar to what happens with IP packets, right? If you have multiple paths from the same router towards the destination, only one path will be chosen based on the flow. And the flow is always based on source-destination combination. So based on the source, based on the destination, a hash is taken, and the Ceph chooses one interface out of the 2, or multiple. So you might have multiple redundant links in your network, in your service provider, but it might so happen that only certain part of the network is being utilized. So you have 3 links, it might so be possible only 2 links are utilized, 3rd one is not, because the hashing is again based on flow. The routers, especially the ones that perform hardware-based switching, do not do per packet load sharing. Only do per flow. Okay? No, so it looks at the source and destination information. Yes. So I believe there is an entropy label that was introduced some time back to do the load balancing over there. Yeah. Any other questions? All good? Yes. Okay. All right. Next important thing, MTU. Your MTU is really important. Now, say for your whole network, the topology that I was showing before had all the MTU consistent 1500 default. From C1 to C2, if I try to ping with size 1500 and I set the do not fragment bit, what happens? Awesome. You guys are right. I didn't bring goodies for that. but we'll still sync up after this. All right. So yes, the packets will get dropped. You need to account for labels, 4 byte each label. So if you have multiple label stacks, like 4 or 5, based on that, you need to account for those labels and set the MTU settings within your network across consistently. You can also set MPLS MTU, which does not change anything from the perspective of IP or the interface MTU, but it accounts for the MPLS headers. Okay? But as a best practice, I would recommend have your network pre-planned in a way that your MTU is consistent across your network, and it is accounting for all the scenarios where you can have multiple labels, 2, 3, 4, whatever it is. Nowadays, I see a lot of service providers are setting the MTU settings to 9216, right? Which is pretty much becoming the standard to have faster convergence and stuff. But having said that, ensure that when you have your MPLS VPN customers, you're not using the same MPLS MTU for them, the MTU size for them as well, because that might not still account for those labels if they send something of the size 9216. Make sense? Yes, no? Okay. So here are the quick tidbits. You can set the MPLS MTU on the interface along with the IP MTU or the physical MTU. If you do not change it, by default it will take it as the whatever the MTU of the interface is, similar to IP MTU, nothing changed there. But you can set it specifically on the interface, any part of your network to further test if there is some issue going on with your MPLS or the packets coming from the customers and it's not accounting for the MPLS headers. Okay? Now, these are the scenarios what happens. So it is similar to what you guys are aware of the path MTU discovery concept, right? Yes, no? Okay. So, and what happens there? You had a question? Oh, okay. Okay. So in path MTU discovery, let me reiterate it again. What happens is the packet from the source, it looks at the outgoing interface MTU and sends a packet. If any of the middle routers before the destination says they have lower MTU, they will say they have only 2 options. If the DF bit is set, they drop. If the DF bit is not set, they fragment it and forward it across. Okay? If they forward it across, and if it's MPLS packet, it will set the MPLS labels on both the packets and send it across, then defragment there. Okay? If the DF bit is set, it will reply back with saying ICMP unreachable because it cannot reach to that destination. Okay? I was discussing with one of the folks here yesterday. If such scenarios happen and you're specifically having BGP with huge number of prefixes updates going on, it is important that you have your MTU setting consistent, not different from MPLS perspective and IP perspective. It should be consistent so that it can account for all the updates, packets that are going through, so that if updates go through and they're not able to make it to the other side, your BGP sessions, especially your VPN v4, can be so impacting, they will start flapping every 3 minutes, guaranteed. Okay? Make sense? All right. So 2 actions. If DF bit is set, drop the packets, send the ICMP unreachable. If the DF bit is not set, fragment the packets, forward it across. Now, the show commands. Some of the show commands are pretty straightforward. Show MPLS forwarding, show MPLS forwarding prefix, detail. You can look at all these information. But the thing I wanted to show you was, if you look at the forwarding table for a particular prefix, you will always see this information, max/ncaps. It will show you the L2 header, and will also show you how many labels are being accounted here. So if there are 2 labels, rather than 18, it will show you 4 more, 22. If it's just single label, like in this case, it is showing 18. It is accounting for the MPLS header. Okay? And in the beginning, I mentioned about the ether type for MPLS packets. Remember? What was the value? Here's the value. You can see it over here. Okay? But you can also see it in the sniffer captures, so either way. But you can always see that information in show MPLS forwarding table. And this is another indication that what the next lookup is going to be. 8847. LFIB. Look at the LFIB, right? Now, are you ready for L3 VPN troubleshooting? This is purely troubleshooting. We are done with all the theory part. I know it's boring sometimes, but all the fun stuff is going to start with this. I said that before as well. Wasn't that fun so far? Okay, awesome. All right, so some of the basic concepts, again, touching base. Provider edge routers, I'll be going through with this, some of the theory and the keyword stuff pretty quickly so that it doesn't get boring for you. We'll go to the fun part quickly over there, okay? The P routers, this is where you're deploying your customers. You're providing services to your customers, VRFs, L3 VPNs, L2 VPNs, L2 circuits to your customers, right? Provider routers, they are BGP free, except for route reflector, unless it is in part of your traffic forwarding, okay? But it's BGP free, and it only does label switching, nothing else. Unless you're doing some regular IP packet ping, it will do IP lookup, okay? C, the C routers, they are also doing only IP routing with the provider edge routers. It can only be, or it can be any of the protocols. There was a question a lot of times I get asked about, is ISI supported for PEC protocol? Well, iOS has ISIS with VRFware. Other platforms do not. But I haven't seen a real customer deployment where they do ISIS on PEC. Okay? So hopefully, if somebody had that question, I already answered. All right, so you can run any of those protocols between the PE and C, and based on that, redistribution will happen, and the packets are forwarded. Now, what happens? Within the core, you run BGP. You actually run MPBGP. You can run a BGP as well, BGP IPv4, but you usually run MPBGP. You run LDP. You can also run MPLS traffic engineering with RSVP. So RSVP-TE, MPLS-TE as well with frost reroute, any of those options. At the edge, you only run with the customer a protocol like BGP, OSPF, RIP, any of those, EIGRP, right? Have anybody of you recently deployed or read about BGP, PEC, IBGP? And do you see any challenge with that? What's that? Well, there's a challenge when you have those ASs and you have to override some of those things on the other side, right? And even for customers who have acquired an AS number from INA and they deploy BGP as the PEC protocol between different with the same service providers, different locations, different sites. Again, they have to go over with AS override functions or allow ASN functions so that they can accommodate for those AS loop prevention mechanism, okay? Any questions? Okay. VRF overview. I think this is one of the most interesting thing that was developed from the virtualization perspective. I mean, you virtualize every routing table segregated from different other components. Global routing table, VRF routing table. This actually helps in using same prefixes by the customer. So they might be 10 customers, each using 192.168.1.0 network in their own internal network, and they can still peer with the same service provider without even exchanging, unless they agree upon, without even exchanging or merging any of those traffic or routes, right? So this actually is used for having or segregating the routing table for each customer with the global routing table, okay? Now, what it does is it's configured towards the VRF or towards the customer, and the core side is running MPLS, IGP, and the regular BGP stuff. So whatever you configure for the customer, any routing protocol, that should be VRF aware. If it's not VRF aware, it will be part of, or if you're just running regular protocol without VRF, it's again going to go in your global routing table, which you don't want, right? So VRF overview, this is again the same thing that I was talking about. Your internal network has, global routing table has 1.1.1.1/24. The same subnet is there on the customer network as well, but they are segregated, right? When they're segregated, you cannot see the same prefix in the routing table. Well, it will only show you from your global routing table perspective. If it's segregated in the VRF, you can only see the VRF prefix in that VRF routing table. So what you do? Yes, sir.
So when the route is exported from the verb
Okay.
to BGP,
Okay.
does the route become a 96-bit prefix with the route distinguisher?
Yes. I'll come to that. I'll be coming to that. You are quick. All right. So as I was talking about, the prefix 2.2.2.2, it's not in the global routing table, it's in the VRF routing table, right? So you can only look at in the VRF routing table. If you go to BGP, now you do not perform a regular IPv4 BGP peering. You can still have it within your network. It's your own network requirement or design, but usually you form VPN peering, VPN v4 address family. So for MPBGP, what it does is it allows for other address families apart from regular IPv4. So there can be others like IPv4 VRF, VPN v4, VPN v6, multicast address families, MDT, L2 VPN, EVPN, any of those stuff. So those are part of MPBGP, okay? Now, the BGP peers, when they form MPBGP session, they exchange VPN prefixes that are, the VPN prefixes that I'm talking about are the prefixes that we learned from customers, but they're not part of your local routing table, okay? We'll see how they are exchanged. So how you configure MPBGP sessions? You configure the peering in the VPN v4 address family, okay? For the peering with the VRF customers or the customers itself, you use the VRF aware address family. So IPv4 unicast, which is VRF aware, okay? Over here. And it's peering with the local C router. Now, what does it involve? So I'll actually skip to the next part to make it more understandable. What I'm talking about is, when you peer MPBGP, three different components are required for MPLS VPN. VRF, within the VRF you have a distinguisher, RD, that you were talking about, that uniquely makes the prefix unique within the service provider network, okay? And then there's the RT. We'll talk about these, all of them, okay? We already talked about the VRF. Now there is route distinguisher. What happens is, this route distinguisher actually is prepended before the prefix, the customer prefix, and is the same value that is assigned for the VRF locally on your router. So this value is, again, local to your router, not remote router. Remote P router can have the same VRF, but a different RD value. It can also have the same VRF, different VRF name, but same RD value, either way, but it's locally unique to the router. It helps in making the prefix unique. Okay? So far good? Any questions?
So does that happen only when it's, when you're exchanging routes, meaning that when it's in a local routing table in that verse, the RD is not dependent at that point?
So when you configure VRF, you need to configure RD. So any prefix in the local routing table, you look at from the local routing table, you do not see the RD value prepended. But when you send it across the VPN v4 or across the MPLS cloud, it is made unique so that it doesn't gets confused with the other prefixes coming from other customers.
So would it suffice to say that probably the most realistic place that you would expect to see that RD dependent would be maybe like a route reflector, because that's
No, you can also see that locally on your router when you look at the prefix from the VPN v4 perspective. So when you do show IP, BGP, VPN v4, VRF, VRF name, and the prefix that you locally learned, you will see the route distinguisher value. I'll show you that. Okay? Yes, sir.
On the route distinguishers, what's the maximum size of, numerically?
So the total prefix actually comes down to be 96 bytes. Okay? The 64-bit route distinguisher. Okay. Route targets. Now, we made the prefix unique, but is the RD same as RT, route target? BGP uses, how does the BGP understand that I need to accept the prefix coming from the remote P router and need to install in a particular routing table, particular VRF routing table? How does it understand that? It's based on the RT, route target. It says, I will export my route with the value, community value, extended community value, I would say, with XYZ, XYZ, and the other guy, if it is importing it, it will be able to install that prefix. So other guy receives the VPN prefix, it looks at the community value, and it says, okay, I have a VRF which is having the import statement for this community value, the RT value, and I will be able to download that prefix into that routing table. That simple. Any questions? So what you do here when you configure VRF, you configure route target import and route target export. You can import the routes from different different VRF tables. So it may be possible like there are two customers, but they agreed upon exchanging their routing information. Or it may be same customer, different sites, they agreed upon changing their routes. In those scenarios, you can import multiple route targets, and you can also export different route targets as well. But the other side should be importing, in order to receive those prefixes, the same route targets. Yes, was there any question? Okay. Okay, so here's an example how RT works. So a prefix, there are 3 prefixes coming with different RT values. 2 of them are same. And the router on the receiving side says import 100:100. The prefixes that are having the route target value of 100:100 on the receiving received from the remote side will import those routes in the local VRF routing table. Okay? Simple. This is how the MPBGP packet capture looks. If you see here closely, you will be able to see the label stack, the route target value, what is the locally assigned label, the RD, and the prefix. Sorry, my clicker doesn't work. So, all this information you can find in the sniffer captures. So when you are doing some research or learning about how the packet flow works in your test environment or viral stuff, you can look into these kind of sniffer captures. Now, we are moving to actual troubleshooting now. I'll be showing step by step how you do a control plane troubleshooting and how you do a data plane troubleshooting. Okay? So far, we only built upon the concepts. Based on these concepts, we'll be able to see how the exchange is working, how the traffic forwarding should be working. Okay? Right. So the first thing, you start by looking at the VPN prefixes received locally and received from the remote P router. Okay? So show BGP VPN v4 unicast summary or show IP BGP VPN v4 all unicast summary, any of these commands you can use. And you'll be able to see in this scenario, 4.4.4.4, this router is the route reflector. So there can be a route reflector for the VPN v4 address family. You do not want full mesh, but you can use RR, okay? And you can see the prefixes received from the remote P router. 2 prefixes. It can be multiple P routers, but in this scenario, it's just one P router, okay? The other neighbor that you see, 172.168.11.2, in iOS, it is also seen as the as part of the VPN v4 neighborship. But it is actually part of, with the new CLI, you can actually segregate it based on the VRF. So show BGP VRF name summary. Okay, you will be able to see the information specific for the neighbors on that VRF, not on the VPN v4. Okay, that was really a good alarm. Thank you. So, all right, so show BGP VPN v4 unicast summary. You want to ensure that information is exchanged on both the P routers, right? Not just one of them. Now, how do you troubleshoot? When you do MPLS troubleshooting, you want to do ping MPLS, okay? Now, if you see here from this output, you can see ping MPLS IPv4 and the remote P router. It is not successful. Any reason? I'll reiterate the topology. C1 router, P1 router, P router, P2 router, C2 router. I'm pinging from P1 router to P2 router, okay? The P1 router is IOSPE, and the P2 router is XRP. Any reason why this ping is not successful? No. RPL? No. So, no. So here's the thing. On XR, you need to enable MPLS OAM. Otherwise, it will not work. It will not allow you to do MPLS ping or traceroute MPLS. You need to enable this. Once you enable this, the ping will be successful. Even though the MPLS LSP is formed, OAM is not enabled. Okay? It was disabled in X. Yes, sir. Sorry, I cannot. No, not really. But usually it's disabled from the perspective because remember I talked about the router alert label, which is CPU intensive, which could be CPU intensive. So by default they disable it, but you can always enable it for troubleshooting. So if you're doing regular MPLS forwarding, you will not see any high CPU. With router alert option, you will be able to see on the RP.
So do you recommend turning this off after troubleshooting?
Well, it's good to have it turned on as long as you're not expecting any, or there's any application which is doing MPLS ping with router alert all the time. There are some applications that try to set the router alert option when they try to verify the LSP. Right? We don't want those scenarios. So if you don't have such applications, there's no harm to enable MPLS OAM. All right, so we verified the LSP path. We are good here. The next thing we verify is the prefix. Now, what do we see in the prefix? We looked at the VPN v4 summary. Prefixes were getting exchanged. Now we go to the XR IOSP router. We look at the locally learned C prefix. What do we see? The important information to look for is these. From where it's getting learned, the C router. What is the RT value? What is the local label? Now remember, this local label will be used by the remote P router to do the forwarding. So any packet that is destined towards CE1 router will have to set the VPN label of 24. 24. Awesome. All right. So I believe there was a question around the RD value, right? How do you see the prefix as unique? So this is locally on the router, and you see the prefix in the VPN table is made unique. right? It's already prepending the RD value. Make sense?
Yes.
Awesome. All right. So once we have checked it on the P router, the local P router, we go to the remote P router. The label that was seen as the in label will now be seen as the out label. Okay? Since this is XR, there's a difference in the output variation, but it still shows the same information. Received label 24. This confirms your VPN labels are getting exchanged properly. Whenever you're doing troubleshooting with MPLS VPN, this needs to be verified. Okay? All right. This is another way to look at the labels very quickly, to look at all the VPN labels. Once this is done, you look for the Ceph forwarding table. So ISP, show IP Ceph, VRF, this will show you the remote PE label, and will show you the IGP label to reach to the next hop, to that remote PE router. So the label 17 here is the IGP label, okay? So you can go to the remote router. So there are other commands that I showed before. I'm not going to repeat all those commands again. But this is how you look at the forwarding table for the IGP prefix. The remote PE router will have the local label as 17. And it will, since this is only one hop before, so it will have a POP label to reach the remote PE router. Okay? This is how you can do the lookup for within the core. On the remote end, what you do is you look for the prefix, the C prefix in the show Ceph. And the Ceph shows the same values, the IGP label and the VPN label. VPN label is 24, IGP label 16. So when the packet forwarding happens, it will have 16 as the top label, 24 as the bottom. And this is the same set of commands to look at how your next hop is reachable and your forwarding information looks like. Okay? Now, in ISXR, you can also verify your hardware programming. Okay? How the things are programmed, not just in software, but from the hardware perspective. So it says, show Ceph VRF, hardware, egress. So when it reaches the egress line card, the outgoing interface, the line card on which the outgoing interface is there, it'll look into the hardware part of it and see what is the label imposition or disposition. Okay? The label information will still remain, should be the same value what you see on the control, the RP side of it, not just the line card. So this is the output from line card. The information that we were seeing before was from RP, the route processor. Okay? Here's a case study. I'll go through it quickly. I believe we are short on time a bit. So here's the scenario where the forwarding from C1 to C2 is not working. P2 is a newly assigned router or deployed router, and the forwarding is not working. What happens is we do a MPLS ping or the trace route, and the trace route actually drops to the hop before the PE2 router. What happens then? Well, this is a common scenario what we run into when you have label allocation for specific loopbacks. In order to save resources on the router, labels are allocated not just for all the links or the prefixes, but specific loopbacks of PEs as well on some of the service provider networks. In that scenario, your outgoing label on the P router, since the ping and the trace route failed, it is showing as no label, right? And further, you look at it from the configuration, you found this configuration. It says, do not advertise labels by default, and advertise labels only for the prefixes defined in the ACL. When you have that, ensure your newly deployed PE routers, loopback is already also added into these, so that proper label allocation is done. Okay? Good? All right. This is something I put together yesterday for your reference. I just added it last minute so that I can touch base upon a few things. The control plane and the data plane within the service provider network, troubleshooting wise, is same what I showed before in this section. We finished, right? In this section, I'm just going to touch base upon the commands and what difference does it make from the VPN v6 perspective for IPv6 L3 VPNs. Okay? So this is the topology that we are seeing here. We have two XR an XR router as a P router and another iOS router. And here you're forwarding, you're exchanging IPv6 routes with the customer. You're providing IPv6 services to your customer along with your IPv4. On iOS, it doesn't work in just IPVRF ABC configuration. You need to change the configuration to VRF definition, which supports for both IPv4 address family as well as IPv6 address family. Okay? On XR, it is not required. I mean, you just add another address family and do the import and export of RTs. Apart from that, nothing changes. Another change from the configuration perspective, rather than VPN v4 for exchanging IPv6 customer prefixes, you now have a different address family, which is VPN v6. And your customer address, customer prefixes are exchanged under IPv6 routing table for the VRF. Okay? Verifying control plane. So control plane part is same as routing. I've put together the commands so that you can refer whenever you want. I'm going to rush through a bit. I apologize for that. I believe I'm running short on time. But the commands, I'll go through a couple of commands which are really important and which will not make much difference from the troubleshooting what we have seen before. Okay? Show BGP VPN v6 unicast. So we used to do show BGP VPN v4 unicast. Now we do VPN v6 unicast and the IPv6 prefix. We see the same piece of information, the local label, out label, RT value, RD value. There's no difference. It works the same way. Only the syntax has changed, right? On the iOS side, you do the same thing. Show BGP VPN v6 unicast. The information exchange is similar to what is there for VPN v4. Okay? The remote P router. So while we are while you want to troubleshoot VPN v6 issues or 6VPE issues, always follow the same path. First you troubleshoot the control plane, and then troubleshoot the data plane from the opposite direction. So verify the control plane information, label exchange, VPN label exchange, IGP label exchange, and then verify your Ceph and your LFIB entries across the path in the backward direction. This will always make it easier to isolate the direction of the problem. The main challenge when troubleshooting is we are not able to isolate the direction of the problem. The problem is in left to right or right to left. This is important, right? So follow the same process. And if you notice here, the Ceph commands are also similar to what we saw for IPv4. So it's only the IPv6 keyword has changed, nothing else, right? Within the core, it is only IPv4. So you don't need to worry about the command line. So whatever we saw from the LFIB path, show IP Ceph or show Ceph forwarding, egress output or ingress hardware output, all these are same. Nothing changes. So I have added a couple more commands for ingress and egress hardware verification on iOS XR so that when you're troubleshooting XR platforms, you can use these commands. Sorry. All right. Any questions here? Now, finally, I actually want to touch base upon inter-AS MPLS VPNs, packet flow. It is important to understand how the packet flow works. Troubleshooting in command line remains same. Okay? But only the concept is the one that is important. So at which point the label change, VPN label is getting changed or exchanged, we need to understand this part. Okay? So inter-AS has three main flavors. Okay? Back-to-back VRF, inter-AS provider option B or option 2, you can say, ASBR to ASBR, and MPBGP RR option. So we'll see what is the actual difference between all these three options. Now, in the first option, so see the scenario as two service providers, and they are having each other as customers. Customer is put in a different VRF interface, VRF address family, and routing information is exchanged. So for them, for this side, AS100, AS200 is the customer, and AS200 side, AS100 is the customer, right? So VRF to VRF, back-to-back VRF method. The label exchange, similar to a regular MPLS VPN setup. Because it is VRF, there will be no VPN label exchange between the two. It will always remain local to the AS. Make sense? Yes, no? I'm not rushing that through. I can still go on for 30 minutes. So please be responsive, okay? All right. Oh, did I move further? Okay, 2A option. Now, in this option, the first option is, and the second option is next hop self method. Now, if you see an arrow on the ASBR routers, I'll point it out, PASBR1, PASBR2, we set the next hop self towards the route reflector in our respective ASs. Okay? What this does is, and also, we also form an MP EBGP session. What is MP EBGP session here? VPN v4 address family. When this is done on iOS, it automatically configures the command MPLS BGP forwarding on the physical interface on iOS. In XR, it doesn't, and it doesn't even require. It only requires you to configure the route policies to allow to exchange the routes. But apart from that, you don't need that. What this does is, it allows the label exchange across those two neighbors, MP BGP neighbors, between the two ASs. Okay? Now, since these ASBRs, if they have VRFs, we are good. The same VRFs that we are exchanging the routes over here for C1 or C2. If they have those VRFs, we are good. If they do not have these VRFs, you need to ensure that you configure this command on the ASBR. No BGP default route target filter. It will not filter those routes and forward it across towards the remote PE on another AS. If it is not there, the remote PE might not be even able to see those routes. Why? Because it will process these routes and try to filter them. It will see it does not have the route target values. And it says, I don't have it, I'll flush it. Okay? So this is important. So I'm reiterating here, no BGP default route target filter should be configured on the ASBRs. And the VPN label exchange, so if you go here, if you look at it from the AS100 perspective, it assigned the label value of V1, VPN label V1, and there's the IGP label. Now, the IGP label forwarding works still fine within the AS. When it comes to the another AS, it has the top label. It will strip off the top label and send the labeled packet to another AS because there's VPN address family. Okay? Now, when it reaches the VPN, another AS, it will say, I am the next hop to its own AS peers. Say, I am the next hop to reach the V1 label prefix. And says, in order to do that, I'll assign my own label because I am capable of assigning labels as well. So in order, if you want to reach me via label V2. So any forwarding, when it comes from P2 towards, in AS200 towards the ASBR, it will come with label value of V2. Okay? When it comes, so after this method, there is, in XR, by the way, this is route target, retain route target all is the command that you use if you are deploying this method. You have a question, sir? Oh, you had a question? Yeah, okay. Any questions? Or did I rush through it too fast?
Quick question. On the last slide there, the top shows the V1 tag on it when it's going in between the ASs. That tag actually is not there?
Which one?
The V1 tag at the top? Is that tag?
So that label is exchanged with V2. So remember, in regular, if there are 3 routers, if label A is being assigned by the middle router to reach B, C, A might also assign a different label to reach C. So if there's any router behind it, it will use the label C to reach to the next. Similar concept. And by the way, same troubleshooting is done. So MPLS ping, you need to ensure your P1 in AS1 is able to ping P2 in AS2. Ping MPLS should work end to end. There is no blocking of it. LSP is complete. As long as the LSP is complete, inter-AS will work just fine. Was there any question? Yes, sir. We'll come to that. It's not here. It's not required in this option. All right, so the next option is redistribute connected. On the ASBRs, in order to complete the LSP, you do redistribute connected. So your MPBG, the link between the two ASs is also redistributed in your local IGP. So you have the next hop information, because when there's an MPBGP session, next hop value changes. Remember, with eBGP, the next hop changes in BGP, regular BGP concept, right? When that changes, the other AS within has the information of the link towards the other AS. So it knows how to reach there, right? And then on top of it, you have MPEBGP session that will do the same work of assigning the label. So the forwarding actually works the same way. V1 label, it sends the stripping off the IGP label, sends the V1 label to another remote ASBR router, and the label exchange happens. The only way the LSP is complete in this section is because of the redistribute connected. Right? See, the concept for MPLS VPN, intra-AS VPN, or CSC is just saying the only thing changes is how you complete the LSP path, how you stitch it. There's no other difference. All the three methods that I'm explaining now are only doing the same thing. Okay? So that's what I spoke about. And yes, you need to configure no BGP default route target filter again. So in this whole option 2, in every scenario, you need to do that. Okay? The third scenario within the option 2 is when you have an eBGP session between the loopback addresses. Now you're doing loopback to loopback peering. Within your AS, you're doing loopback to loopback peering, but even between the two ASs, you're doing eBGP multi-hop to have the reachability information exchanged with the remote peer. You following me or no? Yes, no? Didn't hear you. Yes. Okay. Right, so same thing, again, no route target filter. When the packet reaches, the update reaches the other side, you do not want to filter at the ASBR, send the updates, change the labels, modify the labels, send it to the peers within the AS, okay? The forwarding works like regular MPLS VPN within the AS. Nothing changes there. The final thing, and the most crucial one, the one that you were talking about, the send label stuff, is in this scenario. When you have a VPN MPEBGP session between the route reflectors of both ASs, okay? And you have a regular eBGP session between the ASBRs. When you have the eBGP session between the ASBRs, you say the both the BGP to allocate labels for the other side, each of the other sides. So for my prefixes, I'll send the label information to the AS100. AS100 will send the label of its own prefixes to me. That's how the LSP gets completed. So this is completing the LSP path, and the information or the prefix, VPN prefix exchange is happening via VPN v4. So that part is taken care at the route reflector. LSP is completed via the link eBGP session with send label. In XR, there is no send label command. So in XR, you need to use a different address family called IPv4 labeled unicast. Okay? So like you're peering between the session, you say address family IPv4 unicast, you activate that, and you also configure IPv4 labeled unicast. That makes it capable of exchanging labels. Yes, sir? No, I think it still works. As long as, no, it will not have that problem, because the send label will take care of that capability exchange. So when you do a send label command, it is exchanging the capability to send labels, exchange labels. So if you have address family one side, yeah, because even in Nexus, you do not have the send label command. You have the same labeled unicast address family. So same thing. Any other questions? Yes, no? All right, so we are done with the session. The only thing in this last one was you set the next hop as unchanged between the route reflectors. That's it. So quick takeaways. Yeah, there are goodies coming up. You guys want to wait? All right, so quick takeaways. Understand the flow, control plane troubleshooting, and the data plane, just opposite of it. Whenever you're troubleshooting, use those MPLS OAM tools. Ensure your MPLS OAM is enabled throughout the path. And that should be pretty much simple to troubleshoot any MPLS deployment that you have in your network. Okay? I would also encourage at the end of a session, do fill out the surveys. If you like something, if you did not like something. If you did not like something, do not fill out the surveys. Just tell me, I'll fix it. But yeah, I mean, I encourage everyone to fill out the surveys and let me know how it did. And if there's something specific, I know I couldn't cover all the topics. I personally believe it should be a 4-hour session. I can talk about it. But maybe in future, who knows? All right? Thank you very much.